So I'm Melissa Middleton. I'm going to be chairing the 7th abstract session, also our last session of the day. So we have 4 fantastic speakers. 2 of these will present 15-minute talks, and then the final 2 will be short 5-minute talks. So I will, for the presenters today, give you a 1-minute warning through the chat. I do apologise, I don't have a rattle like Xi Qing. So please keep an eye out for that. And I ask everyone to please direct their questions through Slack. So firstly, we have Ziyang Tol, who will be talking about Ising similarity regression models. So please, Ziyang, take it away.
Thanks, Melissa. Let me share my screen. Yep. So can everyone see my screen?
So I can't see anything shared just yet.
Okay. Is it working?
No, maybe try resharing.
Okay. How about now?
Yes.
Okay. Right. Right. So hi everyone. My name is Ziyang, and I'm a PhD candidate at the Australian National University. So today I'll talk about the Ising similarity regression model, which is a joint work with my PhD supervisors, Dr. Francis Hui and Dr. Tao. Right. So here's the overview of my today's talk. Let me get started with the introduction of our work. The main motivation for our work here actually comes from the US Senate roll call voting data set. So in this data set here, we have this binary response matrix, which we have a total of n different bills indexed by I. And for each of the bill, we have a total of p senators that is voting on each of these bills. So there's the response matrix here, and the senators will use the index J to denote the senator. And on top of that, we also observe another matrix. So the senator attributes matrix here, where for each of the senator, we have observed a ZJ vector. So the ZJ vector here represent the senator attributes for the J senator. And here, for each senator, we observe a total of capital K number of attributes. So based on this kind of data, the research question that we would like to answer here is, how does the similarity in the senator's attributes affect their voting dependent structure in this roll call voting? And so for this kind of multivariate binary data, we have this Ising model. So my Ising model is basically the a model for this multivariate binary data with the following probability mass function. So here Z data is just a normalization constant, which ensures that your probability mass function would add up to 1. And these theta JJ are just your main effect parameters. And the more important ones are these theta JJ prime. So these are what we call the pairwise interaction effect parameters. So we can further collect all these theta JJ prime in a P times P interaction matrix. And this theta JJ prime just captures the conditional dependence between your responses Yij and Yij prime, given all the other elements in the same response vector Yi, right? In the literature, there have been many approaches that have to study the estimation of the theta matrix, the interaction matrix. However, this study here do not directly link the conditional dependent structure to the additional information that we have in the ZJ vector. So, for example, in our case, the senator's attributes. So because of that, based on the senator's attributes, firstly, we can construct the based on the ZJ vectors, we can construct a total of k different similarity matrices, which is denoted by this WK. So because we have capital K number of attributes, so we have we'll have capital K number of similarity matrices, 1 for each attribute. And then, so depending on whether the attribute is a quantitative variable, if it is a quantitative one, then the similarity can just be defined as a decreasing function of the distance between the quantitative attribute of the 2 senators, for example. If it is a qualitative variable, then this similarity matrix can just be constructed using a pairwise comparison, right? So other than this kind of similarity matrix, in certain cases, we have what we call an adjacency matrix. So for example, in network analysis, we might directly have this kind of definition for your WK, which is called adjacency matrix, where if the J and J prime senator are connected in a network, then we just set their similarity as 1. Okay, so this will also be used later on in the real data application part, where we look at the Twitter network of the senators. All right, so now I'll go into our model. So the Ising similarity regression model is basically an extension of the standard Ising model. So we can see that the only part that has changed is this part. So we basically model the theta JJ prime, which as the linear combination. So as a linear combination of the similarities that we just discussed. And these alpha k's are what we call the regression coefficients, which will need to be estimated together with all these other theta JJ parameters, the main effect parameters. And another way to look at this is you can also write this interaction matrix theta as a linear combination of all these symmetric matrices. And those theta JJ and alpha k would just be the coefficients. Okay, so this regression coefficient alpha k here quantifies how the similarity in the Kth attribute of the J and J prime senator affects the conditional dependence between the two senators themselves. Okay, so our aim is to make use of the estimated value for this alpha k to allow us to draw a link between the similarity and the conditional dependence among the senators. Okay, so this proposed model here is actually related to other methods in the literature, which link a matrix parameter to a linear combination of symmetric matrices. But in most of these cases, the theta matrix that they consider is a covariance matrix. So in our case here, it's not a covariance matrix; it's just an interaction matrix that we just discussed at the beginning. Okay. And one thing to note is that the Ising similarity regression model that we propose actually includes the standard Ising model, the usual Ising model as a special case, if you carefully define the WK matrices and also the regression coefficients, then you can get back to the usual standard Ising model. Okay, so now the next part, I'll talk about how we can estimate the main effect parameters together with the alpha regression coefficient. So in Ising model, one of the problem is that you can't use maximum likelihood estimation. And the main reason for this is because of the fact that it will involve the calculation of this normalization constant, and it will which is a sum of 2 to the power of p terms. So when your p, which is the dimension of your response vector, or in our case, the number of senators is large, then this is not feasible. So what we will do instead is we make use of the pseudo likelihood estimation to maximize this pseudo likelihood function. Okay, so this fj here is the conditional probability mass function of the yij given all other elements in the same response vector. Okay, so this is what we call the pseudo likelihood function, and this is so this would give you the estimate for your parameter. But on top of that, we will also like to perform some regularization on the alpha vector, because in real practice, you might have a huge number of similarity metrics, and hence you have a large dimension of alpha. So we want to perform some regularization. So to do that, we just propose the following. We propose the so-called regularized pseudo likelihood estimator, denoted by theta hat, and it's obtained by minimizing the following objective function. So the first part in blue here is the pseudo likelihood function that I mentioned in the previous slide, and you will see that this pseudo likelihood here actually has a very similar form as the likelihood in the logistic regression. And the second part here is what we call the adaptive lasso penalty, and this is the part that will perform the regularization on alpha k. Okay, for this adaptive lasso penalty, we have these adaptive weights. So the WK weights that we will use here is 1 divided by the absolute value of alpha bar k. So alpha bar here is just the unregularized version of this pseudo likelihood estimator, which can be obtained by setting lambda equals to 0. And for the lambda, which is the tuning parameter that will need to be selected, we select this based on a block cross validation. So I'll talk more about this in the next slide. So because, as I've mentioned, because the pseudo likelihood function has a similar form as the logistic regression, so to obtain our estimator is actually we just need to fit a regularized logistic regression to this. So here we have this Y vector, which is a stacked response vector from which consists of the responses from all senators and all bills. And this X matrix here is constructed and then put into this expression here, which gives us the model matrix for our logistic regression. So this Kronecker product part is corresponding to the previous part here, theta JJ. So the Kronecker product is the part that corresponds to this is like an intercept for each senator, denoted by indexed by J. Okay. And as for the block cross validation, to do the block cross validation, we just split these elements into different blocks. And the reason for using blocking here is because in the Ising model, in the same yi vector, all the elements are correlated. So when you are doing block cross validation, for example, we collect y11, y12 up to y1n, up to y1p, and we put them into a same block, and then we perform cross validation on those blocks. So we'll end up with a total of n blocks representing the n different bills. Right? So because of the limitation in time, I will not go into details of the theoretical results, but briefly, we proved the estimation consistency rate for the alpha bar, which is the unregularized version of the pseudo-ladder estimator. And then on top of that, we proved that the regularized estimator, which is the alpha hat, has a faster convergence rate than the unregularized version. And also the regularized estimator is selection consistent. Okay. And now I'll briefly talk about some simple simulation study that we conducted. So here we conducted simulation study based on different sample size n and also different dimension of the binary response vector p. Here k represent the number of similarity metrics, and only the first 5 are truly important. Okay. So and also for the similarity metrics, we just simulate the distances randomly from uniform distribution, and we just use this exponential negative distance squared as the similarities. So we compare 3 estimators, so the regularized and the unregularized estimator, and also we compare it to the Oracle estimator. So the Oracle estimator here is the estimator that has the additional information of knowing exactly which alpha is or which WKs are important. Okay, so theoretically it should be the best one. And this is the estimation performance. So we can see that for our regularized estimator, it always outperforms the unregularized estimator. And on top of that, when n and p gets larger, we find that the regularized estimator gets closer and closer to the Oracle estimator in terms of the mean square error for alpha and theta. Okay, so that shows that the regularized estimator has a good estimation performance. And we also look at the selection performance, and the conclusion is that the regularized estimator has a good selection performance, since the true positive rate tends to 1 and the false positive rate tends to 0 as n and p increases. All right, so finally, I'll talk about the application that I mentioned in the beginning. So we have this data set that consists of the binary voting of US senators. We have a total of 100 senators on 138 bills. And on top of that, we constructed similarity and adjacency matrices for the following attributes of the senators. So the last 3 here is based on the official Twitter of the senators. And the estimation results for the regression coefficients for those similarity or adjacency metrics is given here. So firstly, we can see that because of the regularization, those similarity matrices that are not important, their regression coefficients are regularized down to 0. And also we find the well-documented state and party effect, that is senators from the same state or senators from the same party are more likely to vote similarly. And other than that, we also find that senators who are both businessmen are more likely to vote similarly. And also senators that share certain follower or followee relationship on Twitter actually also are more likely to vote similarly based on our estimation results. Here we have a negative coefficient, and after our further investigation, this is probably due to some sort of matrix multicollinearity, because we actually fitted another model which only include these metrics, and we find that these coefficients turns out to be positive. So that's probably because of multicollinearity. And so here is just some plots, some weighted graphs. So the first 3 plots are the weighted graphs for the state, party, and the Twitter metrics. So other than that, we also plotted the theta matrix. So this is our final theta head matrix in the Ising model, which is given of this form, right? And we can see that other than the usual state and party effect, we also have this, we have connections of senators from different state or different party through the Twitter interaction. Okay, so yeah, so that's to conclude. Based on our previous plots, our model is actually different from the usual graphical structure analysis, which aim at revealing the dependency structures among responses. So our model here actually quantified how does the different senator attributes influence their dependent structure, right? Yeah, so I only have 30 seconds left. So yeah, so this is just the contribution of our work. So some possible future work that could be considered is that we can possibly extend our model to allow for correlated observations. So just like time series data or spatial data, or we could also consider other penalty function other than the adaptive lasso penalty in our regularized estimate. Right. Yep. That's all. Thank you.
Great, thank you, Ziang. I'm having a look on the Slack and I'm not seeing any questions. So unless there's any questions online, if someone would like to unmute themselves and ask the question, I might, in the interest of time, move on to the next speaker. So thank you again, Ziang. That was a great talk. And now we're going to hear from Ziang Liu, who will be talking about increasing cluster size asymptotics for nested error regression models.
Yep, thank you, Melissa. So I just start to share my screen. Can you see my screen?
Yes.
All right. Okay, so today I will talk about increasing cluster size asymptotic for the nested error regression model. And I will split to 5 parts. First one, introduce the nested error regression model and the motivation and how to obtain the asymptotic result and the asymptotic theorems, and also give some examples, including simulation. And first of all, so nested error regression model is called the random intercept model, and we suppose Yij and Xij is from the JF observation from IP clusters, and Yij is scatter response variable, and Xij is a vector explanatory variable. So this one is the expressions for the nested error regression model. And look at that one, we have an index Ij, and I here we just represent the number of the clusters 1 to G, and J equals 1 to Mi. So it's for the I cluster size, and the total amount of the observation is n, summation is I equal to 1 to n to equal Mi. And look at the first part, we just call this one mu Xij is the conditional means of the response given the covariable Xij, also called the regression functions, and beta naught is intercept and beta s, so it's number of parameters. And look at that one, this one is a bit different from the traditional regression models. We have 2 parts, random, we call this part as random part, and alpha is a random effect, and the Eij is the error terms. So in our study, we just let alpha is IID with mean 0 and the sigma alpha square, and the Eij is mean 0 and sigma e square. So look at that one, we not require the normative for the alpha I and Eij. And why is nested error regression model useful? And this one is just useful to realize the value of the random effects. It's very important in some prediction problems. If not, we will treat this part as error part, so it will take like the classical regression models. And when we use the nested error regression models, when the true parameters omega is known, so the best linear unbiased plot predictors plot for alpha I is these expressions. But if omega is unknown, so it will be estimated by the empirical one, and then it's just replaced by the normal maximum likelihood or restrict the maximum likelihood Remo omega heads. So just substitute the omega head here. And but here are some problems here. When we calculate E blobs or E blobs, it is only the point predictions or point estimators. And to measure the prediction uncertainty, approximation to the prediction mean square error are usually used, but they are also required normality hold, and for the G goes to infinity, but the MI cluster size bounded. And John in 1998, he gives some conditions to obtain the consistency results for empirical distributions of E-blobs, but there are no results for the asymptotic distributions for the E-blobs. And in our study, we want to obtain the asymptotic results for E-blobs when the G goes to infinite and all the cluster size goes to infinite. And currently, there are some asymptotic study. The first scenario is the G goes to infinite, but MI is bounded. And maximum Ramo asymptotic is from the Hardy and Rao, Henderson and Miller, and all Lahiri and Richardson and Welsh. But the random effect alpha cannot be consistent because look at that one. We already send the conditions of the cluster size bounded, and the second scenario is a number of clusters bounded, but the cluster size goes to infinite. We can obtain asymptotic result for the estimating parameters such as sigma E square, but not for the between class parameters such as sigma alpha square. And the third scenario is both clusters and the cluster size goes to infinite. And Xie and Yang 2003, they studied asymptotic for the generalized estimating equations, but their results is for the M estimation is not applied for the hierarchical linear mixed effect model. So it's not work for next error regression model. And so far there are no results for the asymptotic distributions for the E-blobs. And what we interesting is the next error regression models with large cluster size, Yij equals to beta naught plus Xij transpose beta S plus alpha plus Ij, and that the G and Mi goes to infinite. What we want to study is a asymptotic result for maximum likelihood and Ramo estimators of beta naught, beta S, and sigma alpha square, sigma E square. And second one is for the asymptotic results for E-blobs. The motivation, as previously we mentioned, that there's no result for the asymptotic distributions of the E-blobs. And also, we know the E-blobs is a point estimators. So if we can get the asymptotic distributions of E-blobs, we want to construct the value prediction intervals for the random effects. And one more motivation is that in this model, we want to extend to a bit general. We don't need to send assumptions about the normality one. And so how to construct the asymptotic distributions for the next error regression models with clusters and the cluster size, both of them goes to infinite. So first one, we just restructure the covariate vector Xij and the slope parameters. Look at that one. In general next error regression model, we write in the Xij here, but we split to two parts. The first one is Xib, so that represents a between covariate, and Xijw is within covariate. And also the similarly to the slope parameters beta S split to the beta 1 and beta 2. Beta 1 is within slope parameters and within slope parameters, so that we can rewrite this one regression functions of mu Xij equals to beta naught plus Xib transpose beta 1 Xijw transpose beta 2. So for example, if we send a single covariate Xij, so regression functions of mu Xij can write down the Xi1 beta naught plus beta 1 Xi if Xij equals 1. Otherwise, it will writing down the beta naught plus X1 Xi bar dot Xi bar and plus beta 2 multiply the Xij minus Xi bar. And the X beta is a summation 1 over mi summation j equals 1 to m Xij. So this one is for this one is just only to represent between I think to vector level cluster levels. So why we want to split to this generate new structure? There's 4 reasons. First one, we can make sure that make the within cluster covariates or parameters orthogonal to the between cluster covariate or parameters, and also allow the corresponding the within and between parameter estimators have a different rate of the convergency. And third one is we not require the centering summations I equals 1 to mi Xij omega W equals to 0. And most important is simplify the calculations. Okay, so this one is for the reason why we construct the model, reconstruct models, and we still need to have two a bit more general conditions. The first one require the finite for plus delta moment for the random effect and errors, because when we send these conditions, we are not required the normality as previously we mentioned. We not require the normality of the alpha I and EIJ, and this one is just only try to satisfy the Newtonian versions of central limit theorems for the alpha I square and the EIJ square in the estimators of variance. And second one, we require the finite 2 plus delta moment for explanatory variables. So this one is just only ensure the convergence of the variance average. And when we send these two general conditions, then we can get the maximum Hall symptotic theorems. Suppose the previous conditions hold, and then that the clusters G and the cluster size Mi goes to infinity, and the solutions omega head is estimating equations of likelihood 1 side omega satisfy k half omega head minus omega dot. Omega dot here is a true parameters that have OP1, where k is previous we mentioned is a rate of different parameters. Look at that one. The first one is the rate is G, is a number of clusters, and the last two is cluster size. So Y1P is a P vector of ones. So it follows that one K half multiply omega head minus omega dot will have it has asymptotic normality distributions with mean 0 and the covariance matrix C. Look at this variance matrix C. This one is a block diagonal matrix, and then we split it for part of diagonal y is 0, and the first block 1 just for the between parameters, and then this one is controller rate from the G, and G1 PB transferred and G. So this one is for the between parameters, between cluster parameters rate, and the second part is for the 1 and multiply 1 vector 1 PW transfer and N. So this one is for the within cluster parameters. And when we get this maximum likelihood asymptotic theorems, and then we can just get the asymptotic distributions for the E block 1. The same, we just send conditions, previous conditions, and let the G over Mi is a ratio of eta I. So that means the clusters of the number of clusters over each cluster size has a rate of eta I, and the eta I can be between 0 and to the infinite when the G and ML goes to infinity. So we define these expressions, and then we have two situations. The first scenario, when eta I is finite numbers, so the G half multiplied alpha I head minus alpha I have the asymptotic normality distributions with mean 0 and the variance sigma E square 8 plus sigma alpha square and HI. And if the eta I goes to infinite, so that we have eta I goes to infinity, that means G is goes faster than the Mi. So that means we have a lot of clusters, but the cluster size are relatively small one. So it will get another symptotic of E block. So Mi half multiplied alpha I minus alpha I has a symptotic normality with mean 0 and the variance sigma E square. So we can rewrite this one as convolution of two distributions, FA and the normal distributions of that one. So F alpha is a distribution of random effect. If our random effect alpha I is a normal dispute, so we can rewrite this one as a alpha I head is a normal distribution with 0 and the variance sigma alpha square plus sigma E square divided by Mi plus sigma alpha I square divided G and multiply the HII. So far this one, when we get this one, we can see the alpha I random effect is no longer the point estimators. This one is consistent, and then we can use that one to generate asymptotic mean square error, and also to generate the prediction intervals for the alpha I. So when we get that one, when we get the approximation asymptotic mean square error and the Kecker and Hartley in 1984 and the Prasa and Rao in 1990, they calculate an alternative mean square error of E blobs. If writing down the general expression is that one, but for specify the expression is very complicated and they have some disadvantage as I show here. The first one is a complicated calculation expressions for the terms M2, and also it requires normality of alpha and EIG. If not a normality, if we without the normality of the alpha and EIG, we cannot Kecker and Hartley, Prasa and Rao, they can write that like these two terms. And third one is point predictions. I cannot justify prediction interval like what we did here, writing down like that one. And moreover, their expressions or approximations, they only allow the G goes to infinite, but the bounded with cluster size like the MI is finite one. And then when we do running the simulation, compare with our approximation with Kecker, Hartley, and Prasa and Rao under unnormative data sets, even look at that one, even the class, this one is a balanced case. We even number of cluster equals 10 and each cluster size equals 10. We have the coverage, look at that one, is very similar and the relative length is similar. And when the G and M goes to infinity, we look at the diagonal area. Look at the G equals 100 and M equals 100. We have the coverage is much better than the Prasa and Rao and Kecker and Hartley, and the relative length is still very similar like the Kecker, Hartley, Hartley and the Prasa and Rao. So it proved in the simulation, it proved that our approximation is better perform as well as the Kecker and Hartley and the Prasa and Rao, but we not require the normality assumptions, and we not require the predictions G goes to infinity and the bounded cluster size. And also right now the random effect E blobs is a consistent estimators, and then we can construct a confident prediction interval for that one. But Kecker, Hartley, and Prasa and Rao, they are only the point estimators, and also like expressions of the approximation is very simple and easy to write down and to do the calculation. And then we just apply to the one random data, and this one is for the asymptotic prediction intervals for the individual random effect representing county vector into area for Massachusetts and Arizona, and the prediction interval are displayed in the QQ plot here. Look at that one. This one is we construct based on our asymptotic distributions of E blobs. And and this is what I talk about, and all the results are published as two papers in JSPI and the JSA1. And that's all what I want to talk about. Thank you.
Great, thank you, Zhang. Very, very fascinating. Now, I'm having a look on the Slack to see if there's any questions. If there are any questions in the room, would anyone like to ask a question? We might have time for a quick question. But if not, again, we are running a couple of minutes over time, so hopefully we can finish up not long after 4 o'clock. So I'll move on to our next talk, which will be from Abhinek Shukla, and he will be talking on the estimation of parameters of two-dimensional shirt model with the product term in phase. Thank you, Abhinek.
Thank you, Melissa, and hello, everyone. So, as being discussed on the title, before introducing my talk, let me inform that you can scan this code, QR code available in each of my slides, and this will directly lead you to my website where you can download all these slides. Okay, so I will discuss parameter estimation of the two-dimensional chirp model. Let me directly introduce the model itself. Equation 1, this represents the decomposition of our data in two parts. The first part is the deterministic one, which is the red colored, and the blue part is the noise error part. Okay. And in the first part, you can see that it is a constant amplitude, meaning by that A0, B0 are free from the running indices. m and n, and inside the cos, there is this phase term of the quadratic polynomial, two-dimensional one, where these parameters alpha naught and gamma naught are the frequencies and beta naught, delta naught are the frequency rates. So our parameter of interest is this whole collection A naught, B naught, alpha naught, beta naught, gamma naught, delta naught, and mu naught. Let me start motivating you for the applications of these chirp models. So if we, since it is a two-dimensional chirp model, we can have a data matrix for a given sample size, and then we can create an image plot in suitably in R software or any other. We get these generated patterns in subfigures B and subfigure C. You can see the resemblance of these patterns with the fingerprints. And next, when we are going to click an image of our desktop screen, we often see that these kind of unwanted patterns appear, which also resemble the chirp patterns. Next, in the Newton's rings experiment, this yellow colored image, you can see the chirp ring exactly available. Furthermore, some applications, these two-dimensional chirp models are being have an important characteristic of interferometric signals or the radar returns. They are used in the 2D homomorphic signal processing, magnetic resonance imaging, optical imaging, and modeling of non-homogeneous texture patterns, digital watermarking, which can further be used in data security. Then neutron rings are used in testing spherical and flattening optical surface and curvature radius measurement. Now let me reintroduce the model. This y is equal to a naught cos plus the error term, a naught cos plus b naught sine plus the error term. What are the available estimation procedures? Well, we can go for the least squares estimators, but the problem is that it will require a 5-dimensional optimization problem at least to solve, because we can eliminate easily these linear parameters a naught and b naught, but we cannot eliminate easily the non-linear parameters. Okay, so solving that will be computationally expensive. The another option is approximate least square estimators. This is again computationally expensive because it will again demand the 5-dimensional optimization problem. Next, we have some suboptimal estimators based on phase differencing and cubic phase function. So there has to be something which is in between, which is not as much computationally expensive as the 5-dimensional optimization problem, but it is also not suboptimal. This is what we are going to target. Now I will discuss only a brief idea about how we have proposed our estimators. Now, if you look at the data matrix at one of the columns, say n naught, you can retransform the equation 1 into equation 2, where in equation 2, it can be seen as a one-dimensional chirp model. So right now, the nonlinear parameters are only 2. Previously, it was only 5. So we have reduced drastically the computational problem for 5D to a 2D problem. And now we can use least squares corresponding to each of the columns and each of the rows, and then we can recover our estimates of the parameters alpha naught, mu naught, beta naught, gamma naught, delta naught. Since we have simplified our problem into a one-dimensional chirp problem, so now let us look at the severity of the finding minima of this sum of squares. So we can look at the least square surface in the part A when there is no noise in the data. So there is a very clear optima there, but in the part B, when we contaminate the data with IID normal 0.5, then we can see that there is very ambiguity creating in the peaks. So these are the assumptions for my for deriving asymptotic properties of my proposed estimators. This XMN is a linear stationary error, and these are some very relaxed assumptions. This is the theorem which proves the strong consistency of the proposed estimators, and then we have this asymptotic normality with these not so usual rates of convergence corresponding to each parameters. We can see that usually the rate of convergence would be root mn, but right now for the nonlinear parameters, this is something higher. And this is the asymptotic variance covariance matrix, and this is the suggested literature if somebody wants to discuss, and these are the references. Thank you, Manish.
Thank you, Avanak. It is very difficult when we only have 5 minutes to talk about such complex topics. So you did a great job. I will remind everyone to please put their questions in the Slack. And we might move on to our last speaker for the day. So please welcome Raunti Utami, who will be talking about joint models for longitudinal and multi-state responses with functional predictors. So thank you, Rianti.
Thank you, Melissa. Can you see my screen?
Yes, it looks good.
Okay, thank you, Melissa. Good afternoon, everyone. I'm Rianti Siswi Utami. I'm a PhD student at the University of New South Wales, Sydney. I'm going to discuss about joint model of longitudinal and multi-state responses with functional predictors. So when should a joint model be used? So it is often that in follow-up health studies, we are interested in observing time to event response and also longitudinal response altogether from the same subject. And it also often that the longitudinal response can be the predictor or biomarker for the time to event response. But then it will raise reverse dependency because not only the event will depend on the longitudinal predictor, but the longitudinal predictor will also depend on the subject survival or the event evolution. Therefore, this reverse dependency needs to be accounted in the analysis. Here is the example where the event of interest is time to Alzheimer's diagnosis and the longitudinal biomarker is the Alzheimer's Disease Assessment Scale Cognitive or ADAS-Cog score. The ADAS-Cog is used to measure cognitive impairment among Alzheimer's disease patients, where the greater the score, the greater the dysfunction. And this is the basic joint model of longitudinal and time to event data with shared parameters from Rhizopoulos. So in joint model, both the longitudinal and time to event responses are modeled separately into submodels. For the longitudinal submodel, it usually uses linear mixed effect model, and for the survival submodel, it uses Cox model. The two submodels share the same parameter beta, and alpha is the coefficient quantifying the association between the longitudinal and time to event data. It is also assumed that given the random FQI, the longitudinal and time to event data are independent. To estimate the parameters in the model, it often uses maximum likelihood estimation by constructing joint likelihood for the longitudinal, event time, and random effect densities, then maximize it with EM algorithm. Here are some developments of joint models. This one is joint model of longitudinal and multi-state responses. It allows for multi-event in the survival submodel. For example, in the Alzheimer's study, if we are not only interested in the risk of Alzheimer's among patients with mild cognitive impairment or MCI, but also in the risk of death from Alzheimer's or other cause, we can use this joint multi-state model where the longitudinal data is still the same, which is the ADAS-Cog score. This model is proposed by Ferrer and his colleague, so the longitudinal submodel is the same as in the basic joint model, while the survival submodel specifies different risks for different state transitions. Here the H and K denote the states in the multi-state model. Another development of the joint model is incorporating functional data as predictor in each submodel. For example, here it includes hippocampal radial distance or HRD as a predictor in the Alzheimer's study. So HRD represents the hippocampal thickness, and Alzheimer's patients have been shown to have smaller hippocampal volumes compared with normal age elderly. So in the joint model with functional predictor, they add functional predictors in each longitudinal and survival submodel. So this is my proposed model for longitudinal and multi-state responses with functional predictors. It is similar with the previous functional joint model, but it allows for multi-state event in the survival submodel. So I combine the multi-state and functional joint model together with functional predictors in each submodel and multi-state event in the survival submodel. Using this model, it is expected to be able to analyze a complex dataset with longitudinal, multi-state, and functional components all together. So for simulation study and data analysis, I'm going to combine the program code from the multi-state joint model and the functional joint model. And currently, I'm still looking for suitable dataset for applying the model. I think that's the end of my presentation. Thank you, Melissa. Thank you, everyone, for your attention.
Great. Thank you so much, Rianti. Now, I believe that is the end of our session for today. And the end of the conference for today. So I'll hand back to Daniela if she has any last minute closing remarks.
Yes, thank you very much, Melissa, and everyone that contributed to your great session today and for the whole day, really. So it's been very good and amazing to see the discussions going on Slack as well. I just would like to remind everyone that we have prizes for the presentation. So we have the Louis Ryan Award for the best presentation. So it's $300, and then second place $200, and third place $100. And also this is for 15-minute talk. We also have prizes for the 5-minute talk. It's $200, $100, and $50 for first, second, and third places. And we also have the People's Choice, which will have a poll tomorrow. And the prize is a SSA t-shirt. And the cash prizes are all sponsored by the Survey Design and Analysis Services, which is our sponsor for the conference as well. And I don't know, Shixing, do you have anything to say about or Lucy, about the in-person tomorrow? Very exciting for people in Perth. I'm sure they'll have a great time there.
Yeah, so for those who are registered and are in Perth, we'll have our bright and early. We'll be starting at 8 o'clock tomorrow. The first session, however, will still be online. So we'll be like a watch party from Perth, and then the in-person talks will start from the second abstract session. But yes, we encourage you to perhaps take public transport or carpool, because there isn't any parking on the local at the venue, but it's a very, very nice venue, which I think you will enjoy.
Great. Thank you very much.
Really looking forward to seeing everybody tomorrow. Just looking forward to hosting everybody and seeing everybody tomorrow.
Yes, we prepared a great day for people in Perth. I'm jealous. So if you can, you should go. Great. See you all tomorrow. Thank you. Thanks for coming.